Alright, in this video we'll be looking at the alkylation of enolate. So we can add an alkyl group to the alpha carbon of a carbonyl compound. That we can we can do this by reacting either enols or enolates with alkyl halide electrophiles. And so if we start with this ketone, and let's say that we used lithium diisopropylamine at negative 78 C as our first reaction, and we follow that up with methyl iodide as our alkyl halide, then we would produce this ketone with this extra methyl group. And that would be the kinetic product. Because the lithium diisopropylamine would prefer to deprotonate at this site, because this is a less hindered site that base can more easily access. And so it can form, the LDA will form that kinetic enolate at nearly 100% yield, and then that kinetic enolate can attack the methyl iodide through an SN2 reaction and pick up this methyl group. Or if we use tert butoxide in T-butanol, then we follow that with the same methyl iodide. Then we would form this ketone with the two methyl groups on the same alpha carbon, because this base, the tert butoxide, would form the more stable thermodynamic enolate, on this alpha carbon, and then that enolate would attack the methyl iodide through an SN2 reaction to add that methyl carbon to that alpha carbon. And again, this works through an SN2 mechanism. And so we need to remember that this will work with primary alkyl halides only. That secondary or tertiary alkyl halides will go through elimination reactions. And as an example of that, we'll show what happens. Again, we'll use this same ketone. We'll use LDA at negative 78. So we'll form this enolate, and then we'll react that with this secondary halide. And what we'll produce will be our original ketone, because that enolate will simply pick up a proton from our secondary alkyl halide plus this alkene, and as we kick off that bromine, that will do an elimination reaction to form a double bond rather than an SN2 reaction to add this alkyl group to our alpha carbon. So this reaction only works with primary alkyl halides. We can use this to form rings. Let's say we have an intramolecular alkylation reaction. And so if we use this ketone, again, we can get two different products depending on what base we use. So let's say that we use LDA at negative 78C. 1, 2, 3, 4, 5, 6, 7. That should be a 7-membered ring. I'm really bad at drawing 7-membered rings. But if we use LDA, then that would pull a proton off of this alpha carbon here. And so that carbon would attack this carbon here, attached to our bromine. And that would give us a 1, 2, 3, 4, 5, 6, 7-membered ring. And it would be the kinetic product because we're using the LDA. If instead of using LDA, we used tert butoxide in tert butanol, then we would deprotonate at this alpha carbon instead of the methyl alpha carbon. We would deprotonate here on this ring, and we would form a 1, 2, 3, 4, 5-membered ring instead of the 7-membered ring. And the ketone would be outside that ring. So here we have this 1, 2, 3, 4, 5-membered ring. And it would be the thermodynamic product. And so this is another case where we can get more than one product depending on what type of base we use. So we'll use, we'll look at another one of these intramolecular alkylations. So now we have a ketone with a methyl group and this phenyl group on this alpha carbon here. And the bromine is located 1, 2, 3, 4 carbons away. And then if we use LDA at negative 78C, then this will deprotonate at the kinetic position on this methyl instead of this other alpha carbon. So we'll deprotonate here, and then this enolate will attack this carbon next to the bromine, and will form a 1, 2, 3, 4, 5, 6-membered ring. With the phenyl group next to our carbonyl. And this would be, again, the kinetic product. If instead of LDA, we use tert butoxide in tert butanol, then you would think we would deprotonate at this alpha carbon, and then this alpha carbon would attack this alkyl halide carbon, and we'd form a 1, 2, 3, 4-membered ring. So we'll draw that out. That this would be the supposed product. The problem is this 4-membered ring has too much ring strain. And so we won't get this product. Instead, what will happen with the tert butoxide is we'll favor, remember that the enolate is a resonance structure where one of the negative charges is located on this oxygen. And so we can react that oxygen with this carbon and wind up with this structure, because this would be the double bond from the enol, and this would be the negatively charged oxygen from the enolate attacking that and forming a 1, 2, 3, 4, 5, 6 membered ring. And this O-alkylation is possible if it can form a stable ring, such as a 5, 6, or 7 membered ring. But O-alkylation tends to be pretty rare. And so this is a case where the alkylation on the carbon isn't possible due to too much ring strain, and so we'll get alkylation on the oxygen instead. There's also a milder way to achieve alkylation at the alpha carbon, and that is called the Stork-enamine reaction. And in the Stork-enamine reaction, we take a ketone. In the first step, we react that with, in secondary amine, with acidic conditions. In the second step, we'll react that with an alkyl halide, in this case methyl iodide. And in the third step, we'll react that with an acidic aqueous workup, and that will what goes on during the Stork-enamine reaction is that we begin by taking our ketone and our secondary amine, and under acidic conditions we form the enamine. And then the electrons from this nitrogen can come down, and we can kick the electrons from this double bond up to attack this methyl iodide, kick the electrons over to the iodine through an SN2 reaction, producing this compound, and then when we react this with acidic aqueous solution, we go through the reverse enamine mechanism to produce the ketone. And in this case, the ketone will be methylated. And so this series of reactions is another way that we can arrive at an alkylated alpha carbon using milder conditions than other reactions we've looked at in this video.